Multivariable calculus, we're looking at 12.2, more work on vectors. First of all, look at this definition right here. When you have a vector A, generally with a vector we'll have an arrow, but very often in a textbook what you'll see is the boldface A instead of having to have an arrow above it. Obviously, handwriting, that's not easy to do whatsoever. So in handwriting, we always use an arrow. But, as you're looking in a textbook, if you're looking on a test or anywhere, even on the web, you might see a bold-faced vector like that. That's why they don't put an arrow above it. But look, you have an x component and a y component in 2 dimensions. Pythagorean theorem would allow you to find the length. This absolute value right here is known as the magnitude of vector A, and of course we could even say the length of vector A. So Pythagorean theorem is the way to do it. Even in 3D, look, you'll see that you just throw in your z component, Pythagorean theorem in 3 dimensions, the square root of your x component squared plus y component squared plus z component squared. Let's see this in action. To take a look at the length of vector u, well, tell you what, we're just going to go ahead and say this is 3 squared plus negative 2 squared plus 7 squared. And that, of course, is 9 plus 4 plus 49. And as we work that out, we know that 4 plus 49 is 53, and 53 plus 9 is 62. And that's going to be your magnitude of vector u. Take a look at this. If you were to multiply 2 times vector u, well, 2 times vector u would just double all of these components, wouldn't it? Multiplying vector v by 3, well, we'd get negative 3, 12, and 24. Then what? You just add these up. Add up your x components. 6 plus negative 3 is 3. Negative 4 plus 12 is 8. 14 plus 24 is 38. And we're done. Likewise, when we multiply 4 times vector u, well, that's going to be a 12, negative 8, and 28. And we could say minus. Well, what's 2 times vector v? Well, we'd get negative 2, an 8, and a 16. And then what? Well, this is just going to be, 12 minus negative 2, negative 8 minus 8, 28 minus 16. And of course, we could have done this in our heads just as well, but that's a 14, negative 16, and 28 minus 16 is going to be 12. So that type of problem, hopefully you can see, is going to go rather quickly. We already talked about the basis vectors. The basis vectors, I, j, and k, go in the directions of the x, y, and z axes. And why do we have that? Well, when you see vector v, you can say, well, that's a, b, c in that component form. Well, my goodness, you could also write that as a times vector I, b times vector j, plus c times vector k. And that would be an IJK notation as opposed to components. Let's take a look right here as we are asked to take vector A and vector B, but multiply 3 times vector A. Well, 3 times vector A would be 3i plus 9j minus 15k. And then we could say, well, minus 4b, we could say plus negative 4b. Negative 4 would get multiplied to each of these. We'd have negative 8i. Negative 4 times a negative 1 is a plus 4. That's plus 4j. And negative 4 times a 4 would be a minus 16k. And then we just add these components together. 3i and negative 8i add up to negative 5i. 9j plus 4j would be 13j. Negative 15k minus 16k would be minus 31k. And this answer is good. Let me tell you, it's just as correct to write this also. So it can depend on what style you're asked to find. IJK notation or in components. Honestly, I really prefer components. I think it goes nicely, but they are both equally valid, and they are both used extensively. So we need to be able to deal with both of them. So unit vectors have a length of 1, and the most famous unit vectors are I, j, and k. But you can make any vector into a unit vector when you divide by its length. And you're going to see that really taking place right here. Let's just take a look at this. Find the unit vector in this direction. This is the vector negative 2, 1, and negative 2 in components, right? And let's just say that I call this vector A. Well, what's the length of vector A? It's not a unit vector. I think we can all agree on that quickly. We'll just use the Pythagorean theorem in 3D right here. And we'll have 4 plus 1 plus 4. And that's the square root of 9, which is 3. So this length is 3. But this is what we can do. We can find a unit vector. The unit vector is really just negative 2, 1, and negative 2. And you're going to say I'm going to divide that by 3. What's it going to look like? Well, really, we should change it into this. What I've just done is I've said, look, I'm going to have my arrow no longer have a length of 3. I'm dividing it by 3, so the length would be 1. I'm going to leave it to you if you're wondering about it. If you did the Pythagorean theorem right here in 3D, if you found the magnitude, you'd find that the length of it was 1. All right. So we're going to finish with this last problem right here. We're going to skip this bottom one. But it says find the component form of vector v of length 3 that makes an angle of 40 degrees with the positive x-axis. And wow, as you begin to look at this, you could think, well, I've got this length of 3, and I've got 40 degrees right here. And really what we need to do is find this x component and find this y component. Now, last year in BC Calc, we worked extensively with x equals r cosine theta and y equals r sine of theta. And guys, I just want to show you real quickly then that we'd have 3 cosine of 40 degrees for our x. Y is 3 sine of 40 degrees. Of course, we'd get this from regular SOHCAHTOA. If you solved, even like you did in your sophomore year, or whenever it was that you first saw SOHCAHTOA. But what is this vector? Well, it's 3 cosine of 40, that's your x direction. 3 sine of 40, that's your y direction. And take it on good faith, I've jotted this down off to the side, just going to degree mode. If you wanted to get a 3 decimal place approximation, you'd find it right here. But that wraps up lesson 12.2, our first lesson in multi.